Hello everyone, and welcome back to what will be our last video for Math 201. In this video, I'm going to kind of continue talking about what we were talking about last week, so some matters like linear regression and such. And what I'm going to do is I'm going to extend what we were talking about last week to look at the case where we have multiple variables. So last week we were looking at the situation where we had a single response variable and we had a single explanatory variable. This time we're going to allow for multiple explanatory variables. Now, this is a topic that is completely optional, so if you have no interest in this topic whatsoever, you have no obligation to bother with this. It's not something that's going to show up on a test or anything, but I include this kind of for your benefit for any research that you might do going forward. Okay, so there are a few topics that I want to cover here, and this is going to be a fairly brief overview to a lot of these topics. If you're interested in any of these, there are more than enough resources available online. There are a couple that I could maybe think of offhand, and if you're interested in these topics, get in contact with me and I can kind of guide you to what you might want to look for. Okay, so the first topic that I want to look at is what's called data reduction. So first of all, let's go and take this matrix of values. So we have four different data points here. There are going to be a pair of values for each. So we have the data point 1, 2, 2, 1, 3, 4, and 4, 3. So what we could do is we could just go and plot our values. And what we would see is that we get these four data points here, 2, 1, 1, 2, 4, 3, or I guess 3, 4, and 4, 3. The idea of data reduction is that you have, well, in this case we only have two variables, but we could have a lot of variables that we're trying to use as explanatory variables. Data reduction will go and change the coordinates that you're looking at to go and cover the most variation in the data. So what's going to happen is that instead of having the typical standard two-dimensional coordinates of your x-axis and your y-axis, what we're going to do is we're going to create a new direction for what will be effectively the first axis, and this axis is going to cover the most variation in the data. So we'll see what we mean with this in just a moment. So to do this, we're going to use a procedure called principal component analysis. So what the principal component analysis does is it goes and finds the axis of most variation in the data. Then what it does is it goes and says, of the remaining directions for the data, find the direction vector that is going to be perpendicular to the first direction vector that's going to explain the next most variation in the data, and then repeat. And what we would see in this case, is that the direction vector that is going to describe the most variation is going to be the line y equals x. And then the second direction vector is just going to be, well, we're in a two-dimensional grid, so it's going to be the line perpendicular to y equals x, which is going to be the line y equals minus x. So if we go and we take our plot, we could go and add two direction vectors. So this first direction vector, so this red line, is going to give us the direction of the most variation in the data. So here what we have is that the data is most varying according to the line y equals x. And then there's only one direction remaining, which is to be perpendicular to y equals x. So the line y equals minus x, such as this blue line here. So what we could do is we could break the So what we could do is we could relabel all of the coordinate axes. So we could relabel from a standard x and y axis to have one axis be the line y equals x and another axis be the line y equals minus x. And this has some very nice advantages which we're going to look at in just a moment. So the first example that we're going to look at is the heptathlon dataset in R, and it's in the package HSAUR. This is a package that is not going to exist by default, but you could install the package with this command install.packages, then open parentheses HSAUR, and R will go and install that package for you. So I'm going to go and load that package. And what we have here is we have a set of heptathlon data, so there are 7 events in a heptathlon, and this is I believe, the women's heptathlon from the Seoul Olympics, which I think was about 1986, 1988, one of those years. So the 7 events that we have are the hurdles, the high jump, the shot put, the 200-meter sprint, the long jump, the javelin throw, the 800-meter run, and then the final score. So the final score combines all 7 of these events, and the athlete with the highest score gets the gold. In this case, that was Joyner Kersee, and then the athlete with the second highest score and so on gets silver, third highest gets bronze. Okay. So one thing to keep in mind here is that the hurdles, the run, the 200-meter run, and the 800-meter run are events where the lowest score is best, but for high jump, shot put, long jump, and javelin, the biggest score is best. So what I'm going to do is I'm going to go and convert the hurdles, 200-meter, and 800-meter runs to be data values so that bigger is better. So what I'm going to do is I'm going to go and take the run time and subtract it away from the biggest time. So the biggest time, whoever finished last. And if we go and we look at these, the results now, what we would have is that this result is saying that Joyner Kersee finished about 7 3/4 seconds ahead of the last place finisher in the hurdles. Joyner Kersee was a little bit over 4 seconds ahead of the last place finisher in the 200 meter, about 35 seconds faster than the last place finisher in the 800 meter. Okay, so what we're going to do for the principal component analysis is that we are going to call the function prcomp, principal component analysis, on our heptathlon data, and we're going to exclude the last column. So we're going to exclude column 8, and we do that with this notation. So we open our parentheses, we have a comma to say that we're taking all the rows, and then we put a -8, which will exclude the 8th column, which is the score. So all we want to do is we want to find the variation among the 7 events, and then you also need to include this parameter scale equals true. So what a principal component analysis does is it takes each of the individual columns and it subtracts away the mean for the column, and then if you include scale equal to true, it divides by the corresponding standard deviation. So what this is going to do is just center and scale all of our data. If you don't include the scale equals true parameter, you can get some rather strange results. So what we'll see here is we get this output from our principal component analysis, and we can just walk through what this means. So we have 7 variables that we were looking at, the 7 events from the heptathlon, and we get 7 components. So what we have in the first component is this is going to be a vector in 7-dimensional space that is going to describe the most variation in our data. Now, the terminology that is used for this is what's called loading. So what this says is that principal component 1 is going to load negatively. So in other words, a high positive value is going to result in a large negative value in the first component. So principal component 1 is going to load negatively on roughly the hurdles, the high jump, the shot put, the 200 meter, the long jump, and the 800 meter. Comparatively to these other 6 events, the javelin's not a very meaningful value, so its coefficient is only about 0.07. The other 6 coefficients are all around 0.4. When we look at principal component 2, it's going to load very negatively on the javelin, a little bit negatively on the 200 meter, and then it'll and then I guess it'll also load negatively on the shot put as well, and it will load somewhat positively on the high jump, the hurdles, and the 800 meter. So in other words, the 3 events of primarily the javelin, but also the shot put and the 200 meter are working in the negative direction. So large scores in shot put, 200 meter, and javelin will give you a more negative value for principal component 2, but a positive value in hurdles, high jump, and the 800 meter will go and give you a more positive value in principal component 2. And we'll go and see a couple of pictures of what this looks like in just a moment to go and visualize what's happening here. Principal component 3 is going to load very heavily on the shot put, a little bit on the long jump and the 200 meter, but mostly just the positive direction is loading on shot put. And then the negative direction is loading heavily on the high jump, the javelin, and the 800 meter. Principal component 4 is going to load very heavily upon the high jump, and then negatively upon the 800 meter, and also somewhat the 200 meter, the other 4 events, kind of negligible loadings. Then principal component 5 is going to load very negatively upon the 200 meter, a little bit on the long jump, and then very positively load on the 800 meter and a little bit on the javelin, and also load heavily on shot put. For principal component 6, it's going to load very heavily in the positive direction on the long jump, very negatively on the hurdles, and I guess the 800 meter a little bit in the positive direction, the other 4 events, not really anything. And then for the 7th component, we'll get negative loadings on the high jump, the 200 meter, and the shot put, with positive loadings on the long jump and the hurdles, and then the javelin and 800 meter aren't that significant. So we can also use the function biplot. So what biplot is going to do is we're going to go and plot, in this case, the first 2 components, and we're going to go and plot each of the individual values. So what we can see here is that Joyner-Kersey's value for principal component 1 is fairly negative, and it's also fairly negative in principal component 2. About the only one of our heptathletes that has a very positive value in principal component 1 is Launa, and Launa also has a very, very negative value for principal component 2. And then what each of these individual arrows are giving you is the relevance of that variable in the first and second components. So if you have a large javelin score, it's going to give you a fairly negative or fairly meaningless result in principal component 1. So we said from principal component 1 is that javelin is going to have a negative coefficient, or a coefficient of about minus 0.07. Impactful but not that big, but a positive javelin score is going to give you a very negative principal component 2, and what we could see is that Launa has a very positive javelin score. So Launa actually, I think, finished at the bottom for the heptathlon, but the one event that Launa did very well in was javelin. Okay. So what we could do is we could go and call a rotation. So R is going to include the rotated values for each of our heptathletes here. So by calling in this case we've stored the principal component analysis results in the variable heptathlon PCA, and going and calling the $X variable for whatever your result for principal component analysis is will give you a rotation of all of the data points based on these new components. So what we could see from this is that Joyner-Kersey is going to get a principal component, or a component score for the first principal component of about minus 4.1. So that's corresponding to this value of about negative 4 here. And then in principal component 2, Joyner-Kersey's score is about minus 1.2, which is also corresponding to what we're getting here. For John, the principal component 1 is going to have a score of about minus 2.8, so less negative than for Joyner-Kersey. And then for principal component 2, John is going to get a score of about minus 0.5, so again, less negative than Joyner-Kersey. And then Launa is all the way down here. So for Launa, we see that the principal component 1 score is going to be over 6, and Launa is about the only one that has a really Launa is the only one that has a very positive score for principal component 1. The other ones are about 2 to 3 or so. And then Launa also has a very negative score for principal component 2, so about minus 2.8. Okay, so then where are these principal component scores coming from? Okay, so what we could do to go and figure out how we could get each of these principal component scores is we could go and look at taking the original values and constructing the individual scores in each component. So what we could see here is that for our principal component analysis, The average for the hurdles is going to be 2.5 seconds. So this is going to be an average of 2.5 seconds ahead of the last place finisher. The high jump is going to be an average of, in this case, 1.78 meters. The shot put is going to be an average of 13, a little bit over 13 meters. The 200 meters is going to be about 2 seconds faster than the last place finisher. The long jump is going to be an average of about 6 meters. Javelin's an average of about 41.5 meters. And the 800 is an average of about 27 seconds faster than the last place runner. And then the scale variable is also going to give you the standard deviation for each of these values. And what we can do is we can take the heptathlon, and we'll take the first row for Joyner-Kersee. And what we could see here is that we get values of about a little bit over 1.5 for the hurdles. The high jump is going to be a little bit over 1. The shot put's about 1.8. The 200 meters about 2.1. So these are giving the standard deviation above the mean for Joyner-Kersee. And then what we could do is we could say, okay, so these are the standard deviations above the mean for Joyner-Kersee. I'm just going to go and store all of these values in the variable line. And then what we could do is we could multiply this vector values in line with the coefficients that we get from the first component. And what we'll see is that we get a score of about minus 4.12, which is exactly what we had for the score for Joyner-Kersee from before. And when we do this for component 2, we'll see that we'll get a value of about minus 1.25. Right, so again, we get this value of about minus 1.25. So this is going and calculating the standard deviations above the mean for, in this case, just our first athlete, and then going and multiplying each of these values, so this list of values for the standard deviations, by each of the corresponding component coefficients. And this is exactly the result that is sitting in the heptathlon X value. So we could go and do the same kind of thing for each athlete, and we would get all of these principal component scores. Okay, so there's also another way of doing data reduction, and it's called factor analysis. So factor analysis is sort of related to principal component analysis, but slightly different. So for factor analysis, you use the function factanal, and in this case, we'll give it again the heptathlon where we've removed the last column, so the scores. But you also have to include the number of factors that you want. So here we're going to include one factor, and we're going to get we're going to again get a set of loadings. So what factor analysis does is that for the coefficients that are going to be very small, it just discards them. So in this case, discards the javelin. What we could get here is that the factor 1 for factor analysis is going to have all positive coefficients. For the principal component, the coefficients were going to be negative. Being off by a minus sign isn't a big deal, but what we could see here is that the first factor for factor analysis, the results are going to be fairly similar to what we had from principal component analysis. The first factor is going to load very heavily on the hurdles, the high jump, the shot put, the 200 meter, the long jump, and the 800 meter, and the javelin's not going to be very important. Okay, so then we could also go and calculate factor analysis for two factors. And what we could see here, and this is a very important observation, is that when you go and you look at factor analysis for two factors, the result in factor 1 are going to be different. So for hurdles in factor 1, we got a coefficient of about 9.52. Now we get a coefficient of 9.68. For high jump, it's about 8.6. Before it was a little bit under 8. And this is a standard result for factor analysis, but for principal component analysis, the factors don't change. So that's why we didn't actually need to give a number of factors that we were interested in, but for factor analysis you do. Now here for factor 2, what we see is also kind of interesting, is that the javelin and the 200 meter are going to load in the same direction, so both are going to be positive. And these are going to be the two variables that are going to be most impactful for factor 2. But when we were looking at principal component analysis, what we saw was that for principal component 2, there, the javelin was the one that had the biggest impact, and all of the other variables were relatively insignificant compared to the coefficient for javelin. So there are going to be some notable differences between principal component and factor analysis, but it does give you two different ways to look at your problem and do some data reduction. We could also go and look at three factors. So what we would see here is that again, the results of the first two factors are going to be different. So that high jump variable, which in just doing one factor was going to be a little bit under 0.8, using two factors was a little bit below 0.86. Now it's back to below about 3/4. And then we also get our factors for factor 3. So factor 3 here is going to load heavily on the 200 meter and the javelin. Now what we see is also very interesting is that the coefficient for javelin in factor 2 went from very important to non-existent. So this is something else to keep in mind when doing factor analysis is the results of a lower order factor analysis do not tell you anything about what you're going to get for one level up. Now with principal component analysis, we had 7 variables and we got 7 factors. For factor analysis, you're not going to get this. So you'll eventually hit a point where you have too many factors requested based on your variables, and in this case, you can't take more than 3 factors. Okay, so then the next thing that I want to look at is linear regression, where we're going to go and look at multiple variables. So first, we're going to go and look at the data using what's called a pairs plot. So the pairs plot is just going to go and plot pairs of variables against each other. And what we could do is go and look for relationships. So here we could see that hurdles is going to have a positive relationship with high jump. So the better someone's doing in hurdles, the better they tend to do in the high jump. Really, we can see that hurdles generally is corresponding to positive relationships with all of these. But when we look at shot put, for example, it's not really clear what kind of relationship is going on with the shot put and the javelin. The 200 meter and the javelin's also kind of all over the place. The long jump and the javelin's all over the place. The impact for javelin against the 800 meter seems to be reasonably constant. But the one that we're interested in is the impact of each of these variables upon the score. So what we want to do is go and try and predict a heptathlete's final score based upon the input of these variables. And what we could see, and this is probably to be expected, the better that a heptathlete does in any one event, the better the score is. The javelin's a little bit scattershot, but outside of the javelin, the rest all seem to have a positive relationship with doing better in the event and getting a better final score. This makes a lot of sense because the final score is based upon how well an athlete does in the individual components. Okay, so what I'm going to do is I'm just going to go and make a linear model very similar to what we did last week. But the only difference is now we're going to have multiple explanatory variables. So we're going to go and build a linear model where we're going to predict the score. So again, remember the notation that we had from last week is we go and put the variable we want to predict first, then we put a tilde character, and then we put our explanatory variables. Here we're going to have the hurdles, the high jump, the shot put, the 200 meter, the long jump, the javelin, and the 800 meter. And we go and combine them just by putting a plus sign between each of the variables. And then the data that this is coming from is the heptathlon dataset. Okay, so we've gone and defined our heptathlon data and we've put it in the variable heplm. And we could call a summary for heplm similar to what we did last week. And what we see here is just a list of our coefficients. So we're going to get a standard intercept of about -800. The hurdles variable is going to not be very significant. So we could see that at the alpha equal to 0.05 level, the hurdles is not going to be significant. So each of these significant codes is giving us how significant the individual variable is. We see that the probability that the hurdles is actually just 0 is going to be about 7%. So it wouldn't be within an alpha equal to 0.05 significance level. So what this means is that we could really go and look at a reduced model where we're going to just exclude the impact of hurdles upon the final score, and we'll do that in a moment to see that things don't change that much. That aside, what we could see is that the hurdles has a very large coefficient of over just under 1200. The shot put coefficient is about the same magnitude as the hurdles, but the probability that the shot put coefficient is actually 0 is much closer to 0. But the probability that the shot put coefficient is actually equal to 0 is very negligible, and it's going to be highly significant. So that's why R is going to give us a 3-star result here. The 200 meter coefficient is going to be significant at the alpha equal to 0.1 level, but not the 0.001 level. And then what we could see is that the long jump, the javelin, and the 800 meter are also going to be very, very significant. So what we could do is we could go and take some results. So we could go and take the scores. Again, we'll just go and look at Joyner Kersee, but you could do the same kind of results for all of the other athletes. So here what we're going to do is we're going to take a vector, which I'm just going to call line, and I'm going to put the first value as a 1. The 1 is going to be dealing with the intercept, so I need to put a 1 in the first position. The 3.73 is the hurdle score, followed by the high jump score, then shot put, the 200 meter, long jump, javelin, and 800 meter. So what I'm doing here with line is I'm going and making a list of values that's going to account for each of Joyner Kersee's values. And then what we're going to do is we're going to take the value in line and we're going to multiply it by the coefficients that we're getting from our linear model. So the coefficients value would just be the intercept value, the hurdles, the high jump, the shot put, the 200 meter, the long jump, the javelin, and the 800 meter. So what we're going to do here is we're going to do an entry-wise multiplication. So I'm going to take this intercept value and multiply it by 1, take the hurdles coefficient and multiply it by 3.73, take the high jump coefficient, multiply it by 1.86, shot put times 15.8, and so on, and then just add that result up, and that will give me my predicted value for Joyner Kersee's final score. So what we can see here is that the predicted final score for Joyner Kersee based on these inputs is going to be rather close to the final score of 72.91. We get a predicted score of 72.57. And again, if you wanted, you could go and do the same kind of thing by going and looking at each of the individual athletes. Now, what we could also just go and do is we could go and use the data reduction that we did from a moment ago to go and also try and predict scores. So what I'm going to do is I'm going to make another linear model where I'm going to predict the heptathlon score, but I'm going to do it based on these scores for the first and second principal components. So remember that the heptathlon PCA is going to store the result from our principal component analysis, and when we go and look at the $X entry, that will go and take all of the data points that we had, rotate them into the new axes that we get from the principal component analysis, and we can go and work with those values. So in other words, what we're doing is we're reducing from 7 variables, so we had the 7 variables from these events that we were using as explanatory variables, and we're going to reduce just down to 2 variables. So we could also go and look at our coefficients here. The coefficients that we're going to get for this linear model are going to have a stock intercept of over 6,000. The coefficient for the first principal component score is going to be about minus 266, and the coefficient for the second principal component score is going to be about minus 50. So we'll do the same kind of procedure. So we could remember that in heptathlon PCA X1, this was giving us the scores for Joyner Kersee that was going to be rotated into the principal components. So Joyner Kersee had that first principal component score of about minus 4.1, second principal component score of about minus 1.2. So I'm going to go and do the same kind of setup as I did before. I'm going to go and take a second line where it's going to be a vector of values where I put a 1 in the first entry, then the principal component 1 score in the second entry, principal component 2 score in the third entry. Now what we're going to do is we're just going to predict the score for Joyner Kersee based upon this reduced linear model. So we're taking the linear model where we're using the principal components to go and predict the score. And what we can see here is we also get a pretty reasonable result. We get about 72.53. The correct scores we said from a moment ago was 72.91. And the predicted score that we had from a moment ago using the full linear model with 7 variables was going to be 72.57. So in other words, what we're saying here is that we've given up very, very little in the predictive power or in our accuracy from our predictions, but we've severely cut our input. So we've cut our input from 7 variables to 2. So another indication about how well your model is doing is with the R-squared statistic, which was one that we said last time. What we could see for the first linear model is that our R-squared statistic is 0.995, so very good, very good correlation, very close to 1. And our residuals are going to be about 47.82. When we go and we look at the linear model where we're using the principal components, our residuals are a little bit bigger. That's not unexpected because we've gone and cut the amount of variables we're using from 7 to 2. So we would expect our residuals to increase a little bit, but our R-squared is still very good. We have an R-squared that's about 0.99, so we're explaining a lot of the variation in our data just by using 2 variables here instead of 7. And what I'm going to go and show at the end of this video is I'm going to show a project that I worked on um, that I kind of was tinkering with over the span of a couple of years. And it's going to put all of these kind of things together. And there what I did was I reduced from, I think, a couple of hundred variables down to about 5 using principal component analysis. So if you're ever in a situation where you can cut your number of variables from something in the hundreds down to something in single digits, that's definitely a success and well worth your time. Okay, and then just to finish off looking at linear regression here, we could just go and look at our residuals. So the residuals we would get from our principal component analysis are going to be given here. So our residual for Joyner Kersey was going to be about 37, the residual for John was going to be about 10, and so on. And our residuals for the heptathlon model, so the full model with 7 variables, what we can see is that these residuals are all kind of comparable. Some are a little bit more, some are a little bit less, but for the most part, they're all in the same ballpark. Okay, so now the next topic that I want to look at is what's called classification. So here what we're going to do is we're going to have a set of data points, and we want to go and put them into various classes. So the data set that I'm going to use is a banknote data set, and similar to before, it's in a package that's not coming by default with R, but you could install it with this command here, install.packages otrmle. This data set is going to describe a set of banknotes where there are going to be 100 genuine notes and 100 counterfeit notes. So the variables that we get in this are the length of the note, the size of the left margin, the size of the right margin, the size of the bottom margin, the size of the top margin, and the length of the diagonal. And then we also get the class, so there are going to be 100 genuine notes and 100 counterfeit notes. We could also go and look at the tail, so this will give us the last 6 entries. One thing that we can notice here is that the genuine notes seem to have a relatively small bottom margin, relatively small top margin, but the forged notes have comparatively large bottom and large top margins. And what we could do is we could go and take a plot for the data just for these 2 variables. So what we have here is a scatter plot where the black dots are going to be all of the forged notes, the red dots are going to be the legitimate notes. And what we see from this is that the legitimate notes have a comparatively small bottom margin, small top margin. The forged notes, for the most part, have larger bottom margin and larger top margin. There's some intermingling here, so we have these forged notes here in the black dots that are very close to some of the red dots, but for the most part, the forged notes are over here on the top, the legitimate notes are here on the bottom. And we could also go and look at a pairs plot for all of our data, where we're going to go and exclude the first column from our data, which was just a class, and we're going to use that class to go and color the points. So again, the black notes are going to be the forgeries, the red ones are the legitimate notes. So what we can see is that these notes kind of have some general trends. So our real notes seem to have smaller left and right margins. The fake notes seem to have larger left and right margins. Um, and in general, for a lot of these variables, the banknote margins or the banknote attributes, they seem to nicely split into the two classes. So it looks a lot like if you were handed a note, you weren't told whether or not it was real or fake, you could go and look at the variables involved and make a pretty good prediction about whether you're looking at a real or a fake note. Okay, so this is all fine, but now let's go and say that we've introduced a mystery note. So we have our data set of 100 real notes, we have our data set of 100 fake notes, but I'm going to go and introduce a mystery point. So our mystery point, I'm just going to go and take the average for the length, the left margin, the right margin, and the diagonal, but I'm going to go and take the bottom margin to be 9.4 and the top margin to be 10.7. We'll see why I've picked those in just a moment. So what I'm going to do is just define another data frame, which I'm going to call banknote 2, and I've taken the data frame from before, but I've added this mystery point. So if we go and we look at a plot based on the top and the bottom margins, we still have our black points up here, so all of our fakes. We have our red points over here, so all of our legitimate ones. But we now have this green point. And what we want to figure out is this green node going to be a legitimate note or a forgery? Because it's kind of in the middle. There are some real notes around it. There are some fake banknotes around it. And this is the task of classification. Is you're given a set where you know what the results are, and then you want to go and take some new data that you haven't seen before, and you want to go and classify it into one of your categories. So in this case, we would be given a new banknote, and we'd want to either classify it as a real note or a forgery. Okay, so one way that we can do this is with what's called the k nearest neighbors approach. So I'm going to take a library called class, so that's going to go and hold the k nearest neighbors function. And what you would do for k nearest neighbors, the idea is to say, well, I'm going to introduce some point, I'm going to fix a number k, and we're going to hold a vote. So when we introduce a new point, we're going to go and find the k nearest points to this new data point. And we're just going to go and find how many of each of those k neighbors fall into each class, and then we'll go and assign the point to that class. So if, for example, we were looking at k nearest neighbors where we were going to take the 5 nearest neighbors, and 3 of the nearest neighbors were forgeries, 2 of the nearest neighbors were legitimate, we would hold a vote, and the forgeries would win 3 to 2, so we would classify that new note as a forgery. So the way we do this is we go and we split our data set with the known results up into a training set and a test set. So in this case, I'm going to take 80% of my values to be my training set, and the remaining 20% are going to be test data. So what we do is we go and we take our training set, and we go and we build the model based on the training set, and then we also have our test set. So we know what the results are for these, and we want to go and predict what each of the labels for the test set are going to be based upon the training set. And then if we go and accurately predict the labels for the test set, that means we have a good model. So I'm going to go and define a variable accuracy, and this is just going to define how accurate I'm going to be for each of the k nearest neighbors, where we're going to go and take various options for k. So the one downside is it's not always clear at the beginning how many neighbors you want to take for your vote. So you could go and take k nearest neighbors with one neighbor, so just find the nearest point, give it that same label. Or you could do 2 nearest neighbors, so you take the 2 nearest neighbors, you hold a vote between those 2 neighbors. Tie-breaking procedure, you can do in a couple of different ways. I'm not going to get into tie-breaking procedure here. But what I'm going to do with this is I'm just going to go and iterate from taking k to be 1 neighbor up to k to be 50 neighbors and see how accurate this is. Okay, so we can go and plot the accuracy. And what we can see here is that we get an error rate of 0. In other words, what this is saying is that it doesn't really matter how many neighbors we take. We could take one neighbor, we could take 50 neighbors. When we hold our vote, we're always accurately predicting the test set. And that makes a lot of sense because what we saw from that pairs plot was that you could pretty nicely break the data into the real and the counterfeit bills based upon the given variables. Okay, so next I'm going to go and do the same kind of thing, but I'm going to do it with a different data set. So now I'm going to use the data set Iris. So Iris goes and has 3 classifications for irises. It is, it's Setosas, Virginicas, I forget what the middle one is. Um, if I call 90, maybe it'll tell me that. And versicolors, that's the third one. So we have 3 categories for our species, and we have sepal length, sepal width, petal length, and petal width for each of the various flowers. And what we want to do is the same kind of thing. So what we're going to do is we're going to take a training set, a test set, and we want to go and try and predict the species based upon the qualities of the sepal length, sepal width, petal length, petal width. Okay, so we'll go and take our data set, we'll go and break it into a group that's going to be 80% for our training set, 20% for our test set. I'll go and define my accuracy as before. And again, we'll go and look between k to be 1 and k to be 50. So let's go and take our plot. And what we can see here is that the accuracy is kind of all over the place. So when we're taking k to be equal to 1, we're getting an error rate of about 3.5%. So what that means is we're miscategorizing a flower about 3.5% of the time. So if we were to try and categorize 1,000 flowers based on this, we would predict that we're going to have 35 are going to be in the wrong category. When we increased our neighbor size a little bit up to about 8, 9, 10, and 11, we were getting perfect accuracy. Then when we're going between about, looks like 19 and 40 something or so, we're also getting perfect accuracy. And our accuracy is kind of fluctuating a little bit in here to go between 0 and 3.5%. So what this is saying is that if we wanted to get perfect accuracy based on our test set, we would want to probably use about, looks like 8 or 9 neighbors to go and use for our vote. Okay, and then we could also go and look at a pairs plot similar to what we did with the banknotes just to see if there are any trends that we could see. So from this, we could see that the black categories, so these are going to be the versicolors, red are going to be the setosas, and green are going to be the virginicas. So from these, we can see the black group is usually off on its own. If we get a value that's going to be in the black category, so we get a versicolor, but we didn't know it was a versicolor, based on these values, it looks like it'd be pretty straightforward to go and say, yeah, based on these values, we have a versicolor. But for the setosas and the virginicas, it's a little bit harder. So there's a lot of intermingling here, especially between the sepal length, sepal width. So there are a lot of overlap between where the red and the green are going to be. Still some overlap in here between sepal width and petal length. Some more overlap in here, overlap in here. So it's a little bit harder to predict which is going to be a setosa versus a versicolor. So that's probably going to be where our misclassification would come from. Okay, so then the final thing that I want to look at here for R is going to be what's called clustering. So this is another kind of idea with classification. The only difference here is with classification, you have labels preset. So you have labels that you want to assign. Here what we're going to do is we're just going to find data points that are, we'll say, common and group them together. So a common way to do it is with what's called k-means clustering. So what k-means clustering does is it creates k groups. Again, you set the k beforehand, and it goes and it puts the data into these various groups. Again, with this video, I don't want to get into the methodology. Um, I don't want to get into a lot of the minutiae about how these procedures work, just because it's going to describe a lot of things that we haven't seen, and you would probably need some linear algebra to really understand what's happening. So I'm just going to focus mostly on the results, and if it's of interest to you, these are definitely things that you should be looking at. And especially if you want to be doing research in biology, chemistry, business too, these are all kind of useful things to know. Okay, so for our k-means clustering, I'm going to go and define a variable range, which is going to go from 2 to 15. So I'm going to go and look at between 2 and 15 clusters. I'm going to define a variable taught SS, so it's going to define the total sum of squares. So this is kind of our error for our clustering. And I'm going to do the clustering based on the iris data. Okay, so now we're going to go and look through k going from 2 to 15, so k is in our range of 2 to 15. We go and we call the function k-means of our data. In this case, we're going to have the iris data with these 4 data points, the sepal length, sepal width, petal length, petal width. So what we're doing is we're looking at points in 4-dimensional space and we're grouping them together based on points that are close to each other. So we take k-means of, in this case, iris, and we're going to remove that 5th column, which was the Virginicas, and we're going to have k clusters. And then what we're going to do is I'm going to put into the tot SS variable the total within sum of squares. So this is going to be the sum of squares within our clusters. What we'd like to do is try to minimize that value. And then I'm just going to have a saved cluster. So this is going to give me the labels for each of the points. And we're going to go and make use of that in a moment. Okay. So we could go and plot our values. So this is going to plot the total sum. This is going to plot the total sum of squares based on more clusters. And as we take more clusters, clearly we can see that the total sum of squares is decreasing. This makes sense because if you eventually took as many clusters as you have data points, you're going to have no sum of square error. So the sum of square is just the distance from the data point to the center of the cluster. Now in general, the way you pick k-means is you try and look for a point where you're not gaining as much anymore. So you look for what's called an elbow. In this case, I'm going to pick 4 because what it looks like is that as I go from 4 clusters to 5 clusters, the reduction in the sum of squares is much lower than it was when going from 3 clusters to 4 clusters. So wherever you see a kind of crook that would look sort of like an elbow, that says that's the number of clusters you should be taking. And what we see here is, we sort of see an elbow around 4. So what I'm going to do is I'm going to make a data frame that's going to hold the iris data set. And I'm going to assign the cluster labels to this data frame. So if I call head of df, we can see that these first 6 entries are getting assigned to cluster 2. My last 6 entries are also getting assigned to cluster 2. If we wanted, we could go and see all of the values that are in. That's my problem. My mistake. I want to assign that. I want to assign the 3rd row. That'll make more sense. So head df. There we go. We get some variation here. So we have 3 entries that are getting assigned to cluster 3, 3 entries that are getting assigned to cluster 4. And we could do a pairs plot where we're going to color our values based on the cluster they get assigned to. So what we can see from before is that all of the, I think these were the versicolors, are getting assigned to the same cluster. But then we're taking some of the Setosas and the Virginicas and we're kind of splitting them up into, we're taking those 2 classes of Virginica and Setosa and we're splitting them up into 3 groups. So you could kind of think about it as the group that we're really certain are Setosas, the group we're really certain are Virginicas, and then kind of this blue group where we're not sure. These were kind of the ones where there was some intermingling between the Setosas and the Virginicas. Okay, so that's all I want to do with R. And now what I'm going to do is I'm going to just come to a different programming language called Python. And this is one that I've used fairly routinely. And what this is a file that's going to look at basketball players based on shot selection. So I can't remember offhand if the NBA keeps this data publicly available anymore. I haven't looked for it in a little bit. But they used to go and include all of the shots that players had taken in every game since the 1996 season. So what I'm going to do here is I'm going to make use of some of the analysis that I just introduced. So primarily I make use of principal component analysis and the k-means clustering. And what I do is I go and I take each player and go and look at the shot type, the shot location on the court. So a court you could break up into a few different regions. Um, the way the shot chart is broken up is it's broken into these color-coded regions. So you have the region in the restricted area, so about 4 feet from the basket. Then you have within 4 and 8 feet from the basket in this blue region. You have the areas inside the paint on the left and the right side, then the area in the paint in the middle. Then you have the areas outside of the paint up to, this is about 16 feet. So these two green regions are kind of forming parts of circles out to about 16 feet from the basket. This yellow region is 16 feet in the middle outside of the paint. Then you have these other 5 regions, which are going to be the right baseline. So long 2-pointers on the right baseline, um, long 2-pointers around the elbows, long 2-pointers in the middle of the court, long 2-pointers on the left elbow, long 2-pointers on the left baseline, 3-pointers in the left corner, 3-pointers on the left wing, 3-pointers straight away, 3-pointers on the right wing, and then 3-pointers in the right corner. So for each of those areas in the court, um, we have various shot types. So you have layups, dunks, hook shots, jump shots, and then also includes bank shots and other kind of shot types as well. And then also a make or miss. So you have a lot of different variables for players. If I remember right, it was in the couple of hundreds. But principal component analysis is going to allow us to rapidly reduce the number of variables that we have. So skipping down to the important things. So for each player, there's a player ID, the player name, the total number of shots taken over all of the years that I have the shot data for, the total number of makes, the total number of misses, and then there are each of the categories. So what we have here is a shot location. So this is going to be above the break, just means above where the 3-point arc breaks from the corner to the arc along the top. The back court, so a shot beyond half court, and an alley-oop dunk, and an O stands for a make. As you could imagine, there are going to be exactly 0 successful alley-oop dunks that are made beyond midcourt for all players. So there's some kind of spurious shot type, shot location pairs, and what I do is I just get rid of them. But then there are other ones. So for example, an above the break left side center, so this would be a 3-point shot on the left wing, and it's going to be a jump shot that's missed. Then we could get a left wing 3-point shot that's going to be a pull-up jump shot that's going to be made, and then I just have all of these kind of shot selection, um, shot location, shot outcome pairings. And in the end, there are 1,300 rows, so that's going to be my total number of players, and the total number of columns is over 200. So there were more than 200 variables for each player. You can imagine that if you're trying to do any kind of analysis on 200 variables, that's probably going to be very challenging, but principal component analysis is going to be very useful here. So this principal component analysis plot is just going and describing the amount of variance described by each of the components. So what we'd have is, once we take all of our 211 components, we'll explain all of the variation in the data, But what we want to do is go and explain a lot of the variation with fewer components. And let's see, so this is also giving the proportion of variance um, that each component is explaining. So the first component explains 14%, the second component explains 8%, the third component explains about 5%, and so on. There's some heuristics on how you would want to choose the number of components to take. Um, in my case, I think I just chose, I want to say 5. Um, 1, 2, 3, 4, 5. No, I think I took 6. So what I have here for the titles are just the various loadings. So what we can see is if I went through this, the first component is going to load heavily on pull-up jumpers and floaters in the positive direction, and the negative values for the first component are going to largely be layups and tip shots, so attempts to put back rebounds. For the second component, the positive loadings are going to be the close shots, so shots around the basket in the restricted area or within 8 feet of the basket, and then the negative loadings are going to be long jump shots, so long 2-pointers or 3-pointers. The third component is going to load positively upon the 3-point shots and also the close shots, but then it's going to have the mid-range 2-point jump shots as going and loading heavily in the negative direction. Okay, and then what I did here is I just printed off for each component the coefficients. So what we have here is a pull-up jumper. So the coefficient in the first component that has the biggest value is missed pull-up jump shots within between 16 and 24 feet, so long 2-pointers, on the right side in the mid-range. Okay, so after using the principal component analysis, I take 5 components, and I go and reduce all of my data down by getting component scores for each of these 5 components. So we've reduced from looking at 200 or so variables for each player to looking to 5. So we've cut our number of variables by a factor of 40, which is usually quite terrific. Okay, so then what I do here is go and look at the proportion of variance that's going to be explained by using K clusters. So in this case, we can see an elbow showing up here at 6 clusters. So after we go from 5 clusters to 6 and then 6 to 7, the proportion of variance is notably decreasing, and that says that to get the most bang for your buck, use 6 clusters. Okay, so then if we go and we look at the 6 individual clusters, um, what we could do here is we could make what's called a silhouette plot. So this kind of gives the level of confidence that you have that each data point is in the correct cluster. When you have values like these that are going to be negative, that says this data point is probably in the wrong cluster, but I don't have a better cluster to put it in, so I'm just going to put it in this one. So you'll get kind of some outlier points where it's not really clear how you would want to classify them. So long as there aren't too many, it's probably not too bad. And what we see here is that for a lot of the data points, we're pretty confident about most of them. Okay, so then this is also going and making a pairs plot for each of the data points. Again, you don't need to know anything about Python or anything that I'm doing here, but this is just another statistical tool for doing a lot of the same analysis we've done in R. Personally, I prefer Python over R, but R's fairly easy to pick up. Okay, so then what I do is I just go and look at the various components and the players that are in these components. So what we have for the first component is the centers. So these are just going to be the centers of where the cluster is going to be. So cluster 1 is going to skew more towards layups and tip shots in component 1, long jump shots in component 2, mid-range jump shots in component 3, floaters and jumpers as opposed to fadeaways in component 4, and then close shots and long 2s in component 5. So the player that is closest to the center in this component is Milt Palacio. I think Palacio played for the Raptors in the early 2000s. He was, an okay point guard. Larry Hughes was another player in the mid-early 2000s with Cleveland and Golden State. Um, some of these other names I forget offhand. Brad Miller was a center for the Bulls. The Bulls, the Kings, and the Pacers in the early 2000s. Latrell Sprewell was a pretty prominent forward who was kind of nearing the end of his career in the early 2000s, but um, see, he would have been playing for the Knicks. The Knicks around 2000, and then I think Minnesota later on. And one quality that we could notice from a lot of these players in the first component, they have a lot of X's. So these are players where the most common kind of shot that Milt Palacio took was a shot in the restricted area that was a missed layup. His second most common kind of shot was a made driving layup. His third most kind of shot was a made layup. His fourth most kind of shot was a missed driving layup, and so on. And what we see from a lot of these players is that a lot of them, their most common shot is generally going to be something missed. And if you're actually going to look at the career field goal percentage for a lot of these players, it tends to be around 40%, which is not very good. In component 2, the player that's closest to the center is going to be Gordon Hayward. Let's see. So then we also get Maurice Spates, Ray McCallum, Jimmy Butler, Carmelo Anthony, Mike Scott, Paul Pierce, Brandon Roy. This component has a lot of the players that are going to be your scorers. So a lot of players that do a lot of scoring, their shot selection tends to be pretty diverse. You'll see kind of some fairly evenly spread out shot charts, and I have some shot charts that we can look at in a moment. Yeah, Markieff Morris, Chris Middleton, Otto Porter, Steve Nash. In the third component, what we would see is a lot of point guards. So Reggie Jackson, Victor Oladipo, Tim Frazier, Jordan Clarkson, Jeremy Lamb, Etuan Moore, Dennis Smith Jr., Terry Rozier. These are all point guards. And what you would see when looking at these is that these players are going to have a lot of shots, mostly in the middle of a court, which makes sense because the point guard is going to have the ball in the middle of the court a lot. The fourth component is going to be mostly three-point shooters. So these are players that most of their shots are going to be three-point attempts. So Antoine Wright, Chase Budinger, Rodney Carney, Dabo Cephalosha, Rodney Price, Randy Foye. A lot of these are kind of players that were more 2010-ish era. Matt Bonner, who had a pretty good following for the Raptors in the mid-2000s, picked up the name the Red Rocket because he would usually show up to the Air Canada Centre by taking the Toronto subways. So the nickname for the Toronto subway is Ride the Rocket, and Matt Bonner is a ginger, so he just became known as the Red Rocket. Let's see, so the next component, these are going to be players that are going to be power forwards and centers. And what's also interesting is that these are going to be power forwards and centers that largely played before about 2008. So these are players that were more traditional big men. They took a lot of shots around the basket, didn't really step out away from the basket that much. Maybe would take the occasional jump shot, maybe within about 15 feet, but that's about all. And then when we look at the last component, we get a lot of the big players who are more recent big players. So these are going to be kind of the stretch tall players. So these are going to be tall players that take a lot of shots around the basket and then also a lot of three-pointers. So the player closest to the center is Domantas Sabonis. Third closest to the center is Pascal Siakam. So a lot of shots around the basket and then a lot of three-pointers. Let's see. So then I have a histogram for the proportion of players in each cluster. So the proportion of players in the first cluster, second, third, fourth, fifth, and sixth. And then what I want to get into just at the end is some shot charts. So this is giving a shot chart for Stephen Curry for the 2013-2014 season, where the more purple a location is, that means the more shots that were taken there. So what we can see is that Curry's taking a lot of shots that are going to be threes, that are going to be straight on, left wing, right wing. Some shots on the left and right elbows, then a lot of layups and a lot of three-pointers in the left corner, not so many three-pointers in the right corner. Then this one is going to be a heat map relative to the rest of the league. So relative to the rest of the league, Curry's taking a lot of threes, a lot of shots in the left corner, not so many in the right corner. Um, Above average proportion of shots taken in kind of that 16 to 20 foot 2 point range, and then kind of a moderate amount of shots around the basket. And we could go and look at a couple of other players just in closing. So I'll go and include Kyle Korver. This is occasionally slow because it does have some generation to do um, to go and cook up all of the graphics and things. There we go. Okay, so what we can see from Kyle Korver, as his reputation precedes him, he's mostly a three-point shooter. What we can see is that most of his shots are three-pointers, a lot of shots in both of the corners, and then wings and straight-on threes. And then for Korver, proportionate to the rest of the league, he's taking a lot of shots in the left and the right-hand corners, a lot of threes on both wings and straight away. And relative to the rest of the league, he doesn't take very many shots inside of the inside of the three-point arc. Let's see. So what's another good one? Uh, let's go and take Kawhi Leonard. So again, it'll take a moment just to generate the images. There we go. So with Kawhi, Kawhi's taking a lot of shots around the basket, and then he's taking moderate amount, moderate amount of corner threes in mostly the left corner, but also kind of the right corner. Um, Relative to the rest of the league, his shot distribution is a little bit more spread out. Pretty above average around the basket, above average in the left corner, the right corner, and then uh, patches where he's going to be above average compared to the rest of the league, below average compared to the rest of the league. Let's see. So one other one that I found interesting was Jose Calderon. I think Charles Oakley might have been similar. Okay, so for Calderon, largely taking shots relative to the rest of the league on the left wing, and outside of that, kind of um, nothing substantively deviating from the rest of the league, a little bit below average around the basket. And yeah, and then the last one that I want to look at is Charles Oakley. So Charles Oakley was kind of at the end of his career in around 2000s. He was very prominent in the early 90s, mid 90s with the Knicks and the Bulls. And then at the end of his career, darn it, I must have discarded Oakley. Okay. That's because Charles Oakley didn't play in 2014. That's the problem. Okay. So anyways, so Charles Oakley, at the end of his career, in the Vince Carter heydays with the Raptors around 2000, so what we could see with Oakley is that his shot selection is very interesting. His shot selection is basically 18 feet from the basket in any direction. And having gone to a lot of Raptors games in the early 2000s, one line that my dad would always say when we would go to games is that when Oakley was in the warm-ups and taking his practice shots, he would always need to be hitting his shots around the elbows of the court. If he was hitting his shots around the elbows, he'd probably be fine. If he was missing in warm-ups, he probably wouldn't hit too many in the game. And what we can see is he pretty much was a kind of single location player, about 18 feet in any direction. Few around the basket, but outside of that, not too much. Okay, and then compared to the rest of the league, as we might expect, Oakley's going to have very much above average shot selection, about 18 feet or so from the basket, and pretty well below average compared to the rest of the league in every other location. Okay, so I think this gives a kind of interesting look at some different things that we could do with R. So kind of building on some of the stuff that we've done throughout the course, mostly looking at stuff that we're going to build on in the last week. Also some different things that we could do. So like data reduction is always kind of useful. And then this gives a nice illustration of some of the ways that we could put all this into practice and also make some nice graphics and things. If you have any questions about this, let me know. We will have a quiz over what we did from the previous week. So looking at our data predictions that we were looking at last week, there won't be a quiz over this material for the most part because we really couldn't even if we wanted to, but it's also extraneous to the course. Outside of that, that's going to be all the content that I have for this course. Next Monday, we'll go and do review, similar to what we did the last week. So I'd go and leave the course time slot open for any questions that you have. My plan is to go and write up the final and get it out to you hopefully by about the 5th, 6th, maybe 7th at the latest. Because of the government shutdown, the exam is formally going to be online. Remember, we're going to use the procedure that I said from before. So I'll go and give you the exam questions. You can go and put in whatever you want into the online test. I'm not going to use it to grade anything, but preferably I would prefer if the answers look legitimate. But what I will look at is whatever you sent me. So we're going to do the test very similar to how we did the midterm. I'll try and make it shorter so that it's not as time consuming. And also remember that the final project is going to be due on the final day of the term. So, so thank you for kind of definitely a strange term, but I hope this was enjoyable and I hope you all learned a lot. Thank you.